All right, everyone. Um, just so you heard all of our names, this is Lars, this is Steffen, this is Tillmann, I'm Sebastian. Today we want to talk about breaking obfuscated .NET malware using profiler-based dynamic binary instrumentation. Just a little bit of background. You might be wondering why the heck are 4 people on this stage. It's because we all 4 worked on this project together, so we also wanted to present it together. We are all reverse engineers working at CrowdStrike, and while my 3 colleagues had, amongst others, the joy of working on this project while attending the CCC, which you can see on the purple picture here on the slide, I sadly had to join them via Zoom while enjoying the sunny beaches of South America. Now, we all have our fair share of reverse engineering experience, mostly focused on x86, but occasionally we also reverse engineer .NET malware, but we certainly wouldn't call ourselves experts, and we had to learn everything on the way as we went through this project. There will be some commands shown on the slides, but don't worry, we'll publish them after the talk. You can find them then on the conference schedule. Now, this whole project started with us coming across a .NET sample that was obfuscated using a commodity obfuscator. As usual, we wanted to get out the strings so we could extract the C2 server. However, the strings were only stored in encrypted form. So we open up the sample in the NSPY, and it kind of looks like this. This is the string decryption function, at least part of it. And what you can see here is it's using mixed Boolean arithmetics. It's using control flow flattening. In short, it's really ugly to look at, and you don't really want to understand it. So we thought to ourselves, well, we'll just be smart. We will use .NET's reflection. We'll call the string decryption function directly. We search for a couple of arguments that are passed to the string decryption function, and we'll get the decrypted strings that way. Now, I have a small demo with me that demonstrates to you what would happen if you would do that. And I pray to the demo gods now. So whatever argument you pass to the string decryption function, you only get back the string x0x. Now, back to the slides. If you scroll further down in the string decryption function, and mind you, this is 100 lines further down, you find this red box, which you can see on the bottom of the slide, which essentially hardcodes this x0x string. And to us, this meant, well, this must be some kind of error state. So we investigated further in the string decryption function, and we identified that this part of the code, don't worry, you don't have to understand it, is partially responsible for us getting back that x0x string. Now, I simplified the code which is shown on this slide to this. And essentially what the malware is doing here, it's executing a stack check. It's basically checking what the type of the caller that's calling the outer wrapper of the string decryption function, what the type is. And since we're using .NET's invoke function, our type is runtime method handle, so we fail at this if condition. Now, of course, we want to bypass this stack check, so what are the alternatives? Well, we could just do the hard work, understand how the string decryption function works, re-implement it in Python, and be on our way. We could try to execute the code in an emulated environment where we would, for example, simulate the stack frame function to return the expected stack frame. We could just try to patch that part of the check in the code and then execute the rest of the code and hope for the best. Or we could use a debugger to manually step through, force the variable values in the way so the control flow takes the intended route. Now, we decided to take the patch and execute approach because we had hundreds of similar samples, so manually understanding the string decryption function for each of those wasn't really an option, and using a debugger wasn't an option either. But you, of course, couldn't have also used the execute in an emulated runtime environment approach. Now, before we design a solution that's too specific to our stack check problem, let's take a step back and look at .NET obfuscation in general. .NET source code is compiled to SIL bytecode, but that SIL bytecode can be, using standard libraries, pretty much decompiled very easily back to source code. Now, because of that very reliable compilation step, obfuscation in the .NET world is pretty much standard. But since obfuscation in .NET is pretty much standard, we as reverse engineers routinely write deobfuscators for .NET, and that obviously leads to an arms race between authors of obfuscation software and us reverse engineers. Now, as part of that deobfuscation process, we as reverse engineers like to execute obfuscated code, so we don't have to emulate the whole thing. And of course, the authors of obfuscation software are trying to prevent that, which is why they include runtime checks, just like that stack check that we saw on the previous slides. But of course, they can get arbitrarily complex. Now, what we want to arrive at as a solution is we want to be able to patch and execute such runtime checks. And to implement this, we opted to use dynamic binary instrumentation at the SIL bytecode level. Now, to implement dynamic binary instrumentation, we opted to do this profiler-based because .NET offers this robust interface for .NET profilers to interact with the Common Language Runtime Environment, or CLR for short. Technically, this works via you writing a profiler DLL, and then the CLR loads that profiler as a DLL and executes callback into it. Now, the Microsoft guide on how to write a profiler basically suggests the following architecture, where you have your profiled process, which has your profiler DLL running, and then you have a profiler user interface that is running in a separate process outside of the profile process, and it's communicating with your profiler using IPC. Now, this design wouldn't have allowed us to directly manipulate the target from our profiler user interface, which is why we opted to move the profiler interface into the profile process. Implementation-wise, we abstract the IPC communication between the profiler and our profiler user interface using a library that we call Dino. And then you, as a user, would write a so-called analyzer that uses that profiler user interface to implement that dynamic binary instrumentation. Now, there is some related work by Antonio Parata that is an alternative to our approach. In contrast to using the profiler interface, Antonio overrides the function pointer in the vtable entry of CLR-JIT's compile method, which is basically responsible for translating SIL bytecode to native code, get triggered prior to JIT compilation. Our approach, however, doesn't require the patching of native CLR components, which is why we could largely implement our approach in managed code. And with that, let me hand it over to Tillmann.
Is this thing on? I love saying that. Okay, hi. It's very loud. Okay, we'll talk a little bit more about .NET fundamentals because we had to learn this stuff, and then we will take an even closer look at the implementation of our approach. So we've seen a version of that picture before. This kind of depicts the lifetime of a .NET instruction. So we write .NET code in a number of languages, in C#, in F#, or Visual Basic. Those are the supported ones. And then this source code gets compiled into an intermediate language that's called SIL bytecode. The SIL bytecode, if we're running on Windows, for example, is what lives in our standard PE executables that get executed. And in the .NET lingo, these are referred to as assemblies. So these assemblies or modules that contain assemblies, they get loaded into the .NET runtime environment. And then we've already seen this blue box here. That's the fundamental core piece of the environment. And by the way, we should mention we are targeting the .NET Core platform. There were other versions of .NET before .NET Core. .NET Core is what Microsoft released in 2016 as open source. And there have been a number of generations since then. I think currently we're on version 9. And I think version 10 will be released in November this year. So .NET Core is what we're targeting here. And yeah, the CLR is the central component here. This is native code, depending on the actual hardware platform that you're running on, that implements a number of core features. And then this provides the runtime environment for .NET assemblies. We have the ones that are compiled from our own source code, but they can also load a number of libraries, such as things for networking, file I/O, and what have you, so that you don't have to implement these things yourself. A component of the CLR, the Common Language Runtime, is this debugging and profiling interface that we are leveraging with our approach. Sebastian already touched on that. And another important element is the just-in-time compiler. We're all familiar with that technology. So compared to traditional compilation process where something gets compiled into native code before it's being executed as a file, In this case, when we invoke a .NET method, that gets intercepted by the CLR. The CLR takes the SIL bytecode and translates it into the JIT takes the SIL bytecode and translates it into machine code that can then be executed on the CPU. This gives us some kind of platform independence. If you are on a different hardware platform, you would just provide a different CLR with a different JIT compiler, just-in-time compiler that does the translation process accordingly. So all really straightforward here. And we want to take a closer look at the JIT here because that offers a number of opportunities that we want to leverage for our approach. So again, here's the process depicted. We start from, for example, a C# source code that gets then compiled to SIL bytecode, and then at runtime, the SIL bytecode for a method, it's all method-based, for a method gets translated into native code that gets executed on the CPU. This has a number of advantages, having a design where you have a JIT compiler. The JIT can, for instance, optimize that code. It can eliminate that code and can do things like loop unrolling and other things that increase the performance of the code. But it can also cache the result. So the native code that's emitted by the JIT can get cached, and then subsequent invocations of that method don't have to trigger the entire translation process again. Instead, they can refer execution directly to the cached bytecode, and then that's another performance improvement or speed up element. Another thing that we kind of had to learn the hard way along the way was that the JIT also performs validity checks. So, for example, if your bytecode messes up the stack or it contains invalid code for whatever reason, then the JIT can say, I'm not allowing this to run. So it performs a number of static analysis checks and says, this isn't valid code. I'm refusing to run that. And then usually you get an exception. Okay, so these screenshots are taken from the awesome dnspy tool. Everybody familiar with that? It's the de facto thing for .NET analysis. It's a user interface that under the hood uses dnlib, a library for messing with .NET assemblies. And I hope it's not too small, but on the top there, there is the decompiled code of a sample application, tiny little method there. And this is the C# representation of that. Now, with the nspy, you can take a look at the SIL bytecode that belongs to that function, and that's the middle box there. So you can see there's an instruction set. You don't have to necessarily understand all the different instructions, but there's an instruction set that's fairly self-explanatory. There's a call instruction, a load string, a nop, and a branch. And that's what the C# code got translated to. This is what is in our file, in our assembly. And then when we execute the SIL bytecode, that's when the JIT translates it to, in our case, 64-bit Intel bytecode. And that's what you can see here. I don't know if you can see the red box, the middle part here, but when that translation happens, the JIT adds a little prologue and an epilogue to the native code so that you can, for instance, I think it's for debugging purposes and so on. But the stuff in the red box is what relates to the actual SIL instructions there. And what we can do now, if we wanted to modify this goes back to what Sebastian said, we can patch something, right? So let's patch the SIL bytecode in the middle, let's patch that and replace all the instructions with nop instructions. So the 5 instructions have been replaced with nops. And then when that gets jitted, we can see that the nops actually make it into the Intel bytecode, right? They're right there. So nops get translated to nops in a different language. And that's great, right? So we could, in theory, I mean, that's very powerful, right? We can do all kinds of things. We can patch the code to whatever we want. But we really don't want to do that manually in a tool like the nspy. We want to automate this. And that's where dynamic binary instrumentation comes in. Okay, so now that we have a fairly good overview of the idea, what we want to achieve, let's take a look at this profiler interface and how we can use that for instrumentation. Quick refresher for everyone, dynamic binary instrumentation, what is that? It is the modification of code, the instrumentation of code at runtime. And usually that happens on the instruction level. I should, by the way, pitch a talk that will happen later today by Holger Unterbrink, He's in the room somewhere. I think he's on at like 4 p.m. and he will talk more about dynamic binary instrumentation in general. So make sure to attend that talk. And what you will see is that what he is dealing with, what he has to do is he has to instrument at the instruction level, because when you're in the Intel world, on the Intel platform, for instance, you have duality of data and code. Code can be data, data can be code, right? It's a von Neumann architecture. So that means that you can have self-modifying code. You can have an instruction that jumps in the middle of itself in an extreme case, right? Or you can have like an XOR loop that decrypts at runtime the following instructions and so on. That's because there's no real difference between data and code. And that makes binary instrumentation on these types of platforms really hard. It's a difficult problem. Now, in our case, we can relax these requirements greatly, actually, because when an assembly is loaded by the CLR, it becomes immutable. So by the time it has been loaded, it cannot change anymore. So the data and code duality doesn't exist. Code is code, and it cannot be modified anymore, right? So what we can do is we can instrument on the method level. Once a method gets thrown on the JIT, the code doesn't change. And that's great, because then we can make our static modifications and patch or whatever we want to do and move on with our lives. So what does that look like if we wanted to do that using this profiler interface that Sebastian mentioned? It's a really nice interface, really powerful. We saw this picture with the boxes with the 2 red arrows. So the profiler has basically two groups of interfaces. One is called the iProfiler information or info interface. That's an interface that allows you to call into the profiler to obtain information about one of the assemblies that are being loaded. For instance, you can say, I don't know, what classes, what types are defined in this assembly. And then the other interface is the iCore profiler callback interface, where the profiler calls back into your application. I mean, it's callback, right? So it's the other direction to inform that an event has happened. And what are the types of events that we're interested in? They are implemented in these callbacks. So these functions in yellow there, for example, the assembly load finished, that's a callback interface that we can implement. So we provide a callback function that overrides this, and then when an assembly load is finished, our callback gets invoked and we can act on the event. And that's quite interesting. So because when an assembly is being loaded or the loading process has finished, then we can say, okay, maybe this is the assembly that we want to instrument and we want to maybe inject certain things or somehow mess with it. Another interesting one is module load finished. So I don't know, the .NET specialists here know this, but a module is essentially a file. An assembly is an abstract concept. So assembly can be made up of multiple files. But in reality, you usually have a one-to-one relationship between modules and assemblies. So when a file finished loading, then maybe we also want to inject certain things and so on. Thread creation is another important one. If we're analyzing malware, which is the kind of stuff that we do, we want to be able to trace threads that are spawned by the main thread and so on, right? And then, most importantly, JIT compilation started. There's a callback that tells us something is being JIT compiled. So this callback allows us to jump into the JIT compilation process, make changes to the SIL bytecode if we wanted to do that, and then the updated code gets JITted instead of the original code. So that's pretty cool. And not only that, there's also, this I think is part of the first interface there, there is a function called setIL function body, set intermediate language function body, which allows us, for instance, in the JIT compilation started callback to say, instead of JITting this buffer, JIT this buffer instead. And there's a prototype implementation of that at the bottom here. So this is an implementation of the JIT compilation started callback that invokes the setIL function body on a buffer. So that's pretty straightforward, right? That's nice. I also want to mention the set enter leave function hooks method. It's a mouthful, but what that does is it allows us to find little stub functions that are being called before a method is entered or before it returns. So, when the JIT compiled bytecode actually gets executed, the native code, we can jump in and say, define an enter hook or a leave hook that gets executed before or right after the function. This can be important if we want to look at return values or arguments and things like that. So we said, this is great. This interface is exactly what we're looking for. Let's do this. Let's write a profiler that we then use for instrumentation. And then, there are a few considerations. How do you go about this? Usually people do this in C++. We didn't want that because, for practical reasons, right? We're in the .NET domain. A lot of .NET code is written in C#. If you, as a person who's developing this, also have to then be familiar with another programming language and know your ways around that domain, that's just another burden. It's difficult, right? So we said, let's try to write this profiler also in C#, which is possible, but there's not many code examples out there, so we had to figure out many of the details ourselves. Now, another element is, regardless of the language that you develop the profiler in, you have to compile it to native code. So the profiler cannot be an assembly because it runs in the CLR. It's part of that blue box where it runs as native code. Now, Visual Studio has a compile target native AOT, so it gets ahead of time compiled instead of just-in-time compiled, right? It gets ahead of time compiled as a DLL, which gets then loaded into the CLR. And then just, I guess, a point of information here. Because of the callback-based interface, the code complexity is pretty high. You have to deal with deadlocks and reentrancy and things like that. So it's not super straightforward to write this code, but obviously it can be done. Okay, so you have seen this picture before. This blue box in the middle there is our profiler DLL that runs in the CLR and interacts with the profiling interface. And then Sebastian already mentioned that we have this other component on the left here, Dino, which is the library, and then the analyzer, which is what the user writes. I guess you can compare it to a pin tool in the Intel world, right? This is the user-provided analytic component, which interacts with the profiler DLL over IPC. And the nice thing here is that everything on the left runs in the .NET context. These are all assemblies, and they run in the same context as our target application, meaning we have full access to it. We can use dnlib to, inspect the assembly, change it, and so on. And then in addition to that, on the right, we have the power of the profiler, so we can intercept the JIT, change code, and things like that. So it's a very powerful design. But it also comes with some challenges that we had to solve. And one challenge is self-instrumentation. Let me flip back to the previous slide here. So everything on the left there gets instrumented, right? Gets traced. So that means our dyno and the analyzer and everything that's related to that. Those things get instrumented as well. And we don't want that because that is the analysis code that we wrote. So we had to figure out a way of distinguishing between the actual target code that we wanted to trace and our dyno components. And the approach that we came up with is a thread-based one. We said, okay, let's execute the target in one thread and then all the analysis stuff, the dyno stuff in another thread. And then we kind of, we mark the threads that are related to our analysis architecture and filter those out. So when we receive an event from dyno or from the analyzer, we filter those out. We don't handle those, and everything else we assume is related to the target, because the target can obviously also spawn other threads. And well, you can see a little code snippet here. Once again, pet example, a JIT compilation started callback that takes the thread ID and checks it against the list. And if it's in that list, then it's one of the ones that we want to filter out, and we just return. So that gives us the ability to essentially ignore everything that's in the red box there. A second challenge is related to just-in-time compilation. So it's actually an advantage, as I mentioned before, but for us it's a disadvantage, and that's rejitting. So I mentioned that the results of a JIT can be cached for performance reasons, but we don't actually want that. We want to be able to intercept every single function call, because maybe the second or the third call is the one that we're interested in, and then we want to jump in and patch the code. So how do we do that? We have to prevent the caching. And we opted for doing that with a function enter hook. So this little thing, this little stub there that gets executed before the actual method gets invoked, we wrote code that nominates that method for rejitting. You can do that. You can say, next time this method gets invoked, CLR, please JIT it again, right? But there's a limitation here. These two stubs, the function enter and leave hook, they cannot run managed code. So the complexity has to be very limited, very low. They have to be super simple. So we designed a producer-consumer concept where the enter hook just puts the IDs of methods we want to read it in a queue, and then there's a second consumer thread just consumes this queue and can run more complex operations on it. So that way we are able to, whenever a method executes, we are able to say, okay, next time that executes, we want to JIT it again, and then we can jump in again. A last challenge that we had to deal with is the injection of calls, of method calls. So imagine there's a method that's being JITted, and now we want to inject a call to a method that we provide into it. We want to inject a call instruction. Similar to other platforms, a call instruction is an operand, and an opcode and an operand. And the operand carries a reference to the function to call. Now, this reference isn't present in our target executable, right? It doesn't know about this function. So we somehow have to be able to inject this reference so that we can later on use it in the call instruction. But I mentioned that assemblies, when they're loaded, they're immutable. So we cannot simply go and inject these references. And an approach that we came up with here uses something we refer to as gadgets. I don't know if that's the best term, but that's what we call it. We prepare a ready-made reference that we inject into every assemble that we want to trace at load time when we can still modify it. And then later on, that reference points to a gadget function that can carry arbitrary logic. So then the user can implement the gadget and do whatever they want using that reference that previously was injected. Okay, now I'm handing it over to Steffen, who will tell you how to actually use this thing.
Cool. That's working? Yes. Okay. So thanks, Tillmann, for these details on .NET internals, and thanks. And profiling, JIT interception, the challenges of self-instrumentation, all that stuff. But to be honest, if I want to use the Dino project, I just want to change SIL bytecode the way I want it to change. So we have seen this before. There is a special component analyzer that you can implement or the user can implement. And all the other stuff, we ship some libraries for that. So you don't have to care about all these details. So this is what an analyzer actually looks like, or how you are going to implement an analyzer. So first of all, you make a reference or make use of the Dino library, and you're just going to instantiate an object of Dino instrumentation. Then you next need to load your target assembly that you want to instrument, and you need to define the actual method that you want to invoke. And in this example here, we are invoking the entry point of the target assembly. So with that minimal code, you are now ready to let the profiler know, okay, please from now on, I want to intercept JIT compilation calls, and I potentially want to make some modifications to the SIL bytecode. Everything other, like the pipe communication, just happens in the background. There's one just more piece missing here in the analyzer, which is this JIT interceptor. And you register this callback with the Dino instrumentation. And what this actually is this callback here. It has or takes several parameters, and the third last one is the most important one. I would say it's a byte array called SIL bytecode. So whenever the JIT in the .NET CLR JIT compiles a new method, now this callback will receive the actual bytes for that method. And within this method, now you are able to do changes to the SIL bytecode array. So I briefly mentioned that before. You need to use some libraries that reflect the Dino, and also you need a library for the profiler itself. Luckily, you can use ship binaries that we can provide, or, I mean, if you don't trust us, you can even compile that. your own, but this requires a little bit more complex build-to chain. As Tillmann said, there's ahead of time compiling and so on. So the easy way, just use the binary, the libraries that we provide. But when it comes to your analyzer, so let's say you implemented an analyzer, we have seen that on the slide before. You implement this JIT interceptor to perform specific changes to the SIL bytecode. Then you just can run .NET publish to compile your analyzer. To execute your analyzer, then you need to set some environment variables. So to let the .NET CLR know this is the particular profiler library that I want to use. And if that is set up, you just can call your analyzer .exe, and you can, for example, here give a path to the target assembly that you finally want to instrument. And whenever you do changes to your analyzer, you develop something, you only need to recompile your analyzer. You do not need to touch the libraries for the profiler or the Dino framework. Okay, so now you might ask yourself, okay, I want to do some changes to the SIL bytecode. How do I do that? So you get a byte array reflecting that SIL bytecode. And I mean, it's an array. You could just go to offset 30 and change the byte value to 50. I don't know, but doesn't really explain what the code is doing or what you want to patch here. So we came up with this concept of target patterns that help you to implement changes to the SIL bytecode. So these target patterns are actually regexes. So they serve two purposes. First of all, you need to, or they help you to identify the actual method that you want to patch. And also we have a little trick to embed the actual byte change that you want to apply here. So let's take this regex example here. So there is a regex that requires an input to start with the byte sequence with the value office. And then this regex defines a group. That group is matching on the value food. And this group has a name, patch to beef. And I mean, you might expect that and guess what this regex is supposed to do. It will patch the value food to the value beef. So if we're looking at the example input here, the example input starts with the value office, contains the value food. So the regex will actually produce an output where food is changed to the value beef. But yeah, just briefly mentioning here, you are not limited to using this regex target pattern. You will later on see more demos that do more powerful things. Yeah, but to not stick to that dummy example of office and food and beef and so on, let's see how these target patterns work in real-world examples. So here we have a C# function that comes from the .NET Reactor obfuscator, and this is doing a date check. So this kind of code usually translates to a SIL bytecode that looks like this. So it shows the end of the method. There are some instructions. So first of all, there is a branch instruction to evaluate the actual date check. And if the date check fails, then it will load an error string. It will create a new exception object and then finally throw an exception because the check failed. So if we want to instrument our method here to always check that, pass that check, what we would need to do is, okay, let's eliminate this throw instruction. So you could just knob it. We have seen that before. There's a knob instruction, but we also heard we need to make sure that the stack is intact and so on. And the throw instruction is popping from the stack. So to make the stack check happy or the compile process happy, we need to replace it by a simple pop instruction. And we can do so if you look at our target pattern. We are effectively in the byte code. We are changing the opcode 7a to an opcode 26. So this SIL bytecode would usually translate to some native code that looks like this. So at the start, you see there is the system exception being created, and then in that highlighted box, there's code to actually throw the exception. So now let's see what happens when we apply the target pattern to patch and eliminate this throw instruction. So let me clear that first. Right. Then sorry. Here we go first. Let's check the code here. Cool. So that is the code that you have seen before. Now we are in the nspy debugger. And I already set a breakpoint to this check here. But first of all, I will show you that if we execute our target, it's this one here. So if we would execute the target, we see an exception that tells us the error string, okay, not passing the stack check at all. So if we now instead use our analyzer, here it is, and pass it the our target again. Sorry, I forgot something. We want to see that in a debugger. So we enable debugging. So again, we call our analyzer. What? I hope so. Yeah. So we are now ready to attach the nspy. Okay, here we go. Now I will continue execution until it hits our breakpoint with the date check here. So this is the date check. This obviously fails because we are not in 2024 anymore. We can look at the SIL bytecode. If we scroll down, remember we are kind of transparently patching in the fly. So we didn't change the assembly at all. So we still see the throw instruction. What we see on the left here is that our analyzer conveniently prints out the instructions for the SIL bytecode that it changed on the fly. So when it really goes to the JIT compilation process, and here we see the effect of our target pattern. So instead of a throw instruction, now the SIL bytecode has a pop instruction. And we also see that here, if we now go to the native code, so if we look at the disassembly of that function, because now it got JIT compiled with our target pattern in place. So here you see the same you have seen on the slides before. There's the exception being created, but it's not thrown at all. It just will continue on execution. So if we continue execution, there is no exception, but some hello world output. So let me prepare. Here you go. Cool. So instead of the regular JIT compilation, we now applied our target pattern, eliminated the exception, and it just became basically a NOP instruction. And now we will see some more cool real-world examples.
Okay, cool. Thank you very much. In this section, we'll go through a couple of example use cases to actually use the framework in the real world, like things that come across that you do during malware analysis, basically. And this is, by the way, what we are focusing on. We are malware analysts in our day-to-day, so this will all live in some sort of malware space. We'll cover 3 demos, and they will kind of increase in complexity over the time. The first one is just a function call tracer. The second one is about decrypting strings, actually the example that Sebastian talked about at the very beginning. And the last one will be about generic payload dumping in a situation of virtual alloc, then create thread. in a situation like that. But really, in my opinion, this is just the beginning. Consider these demos proof of concepts. They can certainly be improved and extended. And there are probably a gazillion other ideas that everyone else probably in this room can come up with, and I'm looking forward to that. So, quick reminder about the situation we are in. You've seen this picture a couple of times by now. The target malware is at the bottom left. All the profiler-related stuff is on the right. And communication with the profiler is done through Dino, which is on the top left. And our task is to write an analyzer, so we are basically exactly here. The purpose of the analyzer is to load the target assembly, enable instrumentation, and run the target assembly, or some part of the target assembly. So far, we only have invoked the entry point, but we could also invoke other methods. And the second demo actually will be about invoking a specific function. And in between, it can do whatever necessary to implement the use case at hand. Okay, let's start with function tracing, and there will be a lot of source code incoming now. What is function tracing, or why is it even interesting? Quickly to motivate it. When you analyze a completely unknown piece of malware, it is a very good starting point to just get a list of functions in the order that they are called, basically scrolling through, to just get a very broad strokes impression of the malware. And Steffen already covered that. Here's the code again for completeness sake. We instantiate the .NET Instrumentation class from Dino, then set up a callback, which we'll cover in a second. It's called JIT interceptor. And then we load the target assembly, which is passed as a command line argument, set up the .NET thread to call the entry point. Finally, we will enable instrumentation, start the thread, join it, and do some cleanup afterwards. But the real business logic lives in this JIT interceptor function. And it's called every time, I mean, you've probably guessed it by now, any function or method is being JITted. And it receives a bunch of metadata for it. And this is something we are interested in this use case, like the thread ID, base load address of the module, method ID, things like that. And we will use that for our function call tracer. And it also receives 3 arguments at the end, SIL bytecode, regit, and bytecode modified. For the function call tracer, the regit thing is most important because that is what Tillmann talked about. Normally, after a method is JITted, it's cached, so it's not JITted again, which would suck for a function call tracer because then we would also see the first call and then no other call, no subsequent call. And what we actually want to do here is not modify the SIL bytecode. So we are not touching the SIL bytecode array. We are also not setting bytecode modified. I mean, we set it to false, but we don't want to modify it. We only want to regit every function. And the only thing that we do is we resolve the function name here and just print it on the command line. Okay, let's go to the demo now. Let me switch the environment. So the function, the program that I will be executing, I will quickly list it here. It's just the main function that is called, and then it calls 2 times the dummy function, which just prints hello world on the console. And yeah, we will now just call our simple tracer. No, wait a second. Didn't pray enough to the demo gods, I guess. There we go. Okay, so we will execute the simple tracer, and then with the target, with a compiled variant of the source code that I just showed you. And here we go. And we can see now here it prints the thread ID, but it also prints a call, the call of the main method, and then the call to the dummy method. And then we see the hello world being printed from the dummy method. And then we see the second call to the dummy method because we set regit to true. So, and then we see another print to hello world, and that's done. So I guess relatively simple to implement this tracer. Okay, next demo. Again, they will increase in complexity, I'm sorry. We are going to cover string decryption next. This is the use case from the very, very beginning that basically motivated this entire adventure. So let's better hope that it works. Otherwise, it was all for nothing. A reminder from Sebastian's part of the call, of the talk. In orange, you can, it's not very visible in orange, there is a string decryption, string deobfuscation function. It has the convenient name hash equals ZV02MJMY, and it receives just a number. And this number is the string that should be deobfuscated and then returned. And these calls to this string deobfuscation functions are littered all over the binary. Obviously, every time it wants to use a string, this method is called. And the method on the inside, Sebastian showed that, is pretty obfuscated. So we don't want to look it up in detail. And and it's rather complex and so on. So, but when you just call the function with a fixed argument for starters, for example, with a number from outside, basically, you always get returned this string. That is what Sebastian showed in his demo. And that's the bane of our existence, basically. And Sebastian also told you that that is because the function, the string decryption function, inspects its own call stack and only returns the correct string if this call stack is valid. And I will exclude more details here, but this is the exact place in the code where this fails. But we now want to write an analyzer that makes that check pass instead. This is how the SIL bytecode looks, and we could do many things here to bypass the check, and we just decided to replace the LD log S instruction in the first line here by an unconditional jump of a couple of bytes, and then the check will pass. And for that, we'll be using the target patterns that Steffen talked about. Note the patch 2 part here in this target pattern at the line 3. This demonstrated one of the design goals of target patterns. They are a bit bulky to use, right? You need to know how instructions are encoded, and then you need to write a regex for the whole function and so on. But they're relatively fast to write. You can just copy the bytes in it, mask out a few offsets or something like that, and then just patch something out, like get shit done TM. So I would say they are rather fast in practice to use. And what is happening here is that we are replacing with a 2B 4A. We are replacing that's the encoding of the LD log one. Oh, wait a second. No, we are replacing the 11 ... That's the encoding of the LD log instruction with an unconditional jump. And when you execute that, you get back to XOX because there sadly is another stack check. And this is the constructor of the class responsible for the string deobfuscation. And don't worry reading this obviously now. I mean, that is just demonstrate that it's also complex again. And what this does, and what we will do is, what this one does, it uses a couple of variables of different types, one of type stack frame, stack trace, and method base. And what we are going to do is we will first check if these local variables of these types exist in this assembly. And then we'll implement a very small state machine that detects this function and then patch out the stack similar to before. But we'll not be using the patch 2 feature of target patterns, but another feature that you notice here in this target pattern. It will match on this function. I didn't print out the SIL bytecode here because it's just a mess. But you can see when this thing matches, it will call the stack check TMP CB function. So that is not using the patch 2 one, but it will call the callback. And that callback can return true or false if it decided to modify the function or not. And it can also obviously then just modify it. And this is this callback function. It uses a convenience function we wrote in the Dino framework that is called get locals by type names, also kind of a mouthful. And that function accepts a list of type names, and it returns a list of local variables if and only if for each of these types there exists exactly one local variable. If it doesn't, it returns null, and then we can early out for performance reasons. But if it does, we now have these 3 local variables. And we'll use 2 of them, the stack frame, the one of type stack frame and the one of type method base. And then we will call the detect and patch stack check function. That is where this state machine lives. And then in the end, we will just rewrite the instructions and return true to signal back to the profiler that we changed something, and then it will do it. And this function, I'm obviously not showing this to confuse you or that you understand it within 10 seconds or anything like that. I just want to show you that you can do arbitrary complex things in these target patterns. So in this case, it just goes over all the instructions of the method body, assumes the existence and usage of these 2 variables that I just talked about, and then returns true or false depending on what if it wants to modify anything or not. And then, so let's zoom out. That was the kind of complicated part. But in general, what we are going to do is we will find the string decryption method. That is just, we wrote a function signature for that. Then we are going to find all call sites of that string decryption method. And that is kind of one of the situations where all came together. So we could now we are just now using dnlib to parse the assembly as a whole, and then easily can find it. The enlib basically does all the heavy lifting for us. We can easily find all the call sites, and then we can find out, also determine the argument that is passed to it, and then we can run it all in the profiler, intercept the JIT, patch out to 2 stack checks, profit. Okay, so let's do the next demo. Change the environment for the second demo. Cool. So this is the analyzer that we just wrote, and now I will pass the original sample that we started with, and I will also, it accepts the second argument where it will dump out all the strings too. So, and that will run for a second, so I can quickly reiterate what is happening. So in the second output line, it found the string decryption method, or it was searching it, then it found it in the next line, it has this name, and then now it's parsing the entire assembly with the enlib and finding all the call sites. That worked. It found around 7,000 of them. Then it also already found all the parameters that were passed to the function. There we do some like backwards, we disassemble it backwards to find like the value that is put on the stack. And there are around 4,000 unique operands passed to the string decryption function. That happens because the malware is probably using the same string in multiple places, and there is always the same operand, but we deduplicate that to basically be a bit faster. And now what's happening, what takes longer, and it takes around 1 minute or something like that, we are calling the string decryption function with all the 4,000 different operands that we saw, and then normally it would return XOX, but because we are patching out these two stack checks, it will just return the string now. I hope. In a second or two. Yeah, and it's printed a couple of example strings, and I open the rest of the strings here in a notepad now, and then you can also see, I know that there is one juicy string in there here at the bottom, and then you can see there is like some sort of C2 address, or at least a network address, so that's cool. All right, so let's go back to the slides. The demos will increase in complexity, so we are finally getting to payload dumping. So let's consider this situation. It's paraphrased from a random delivery tool probably used by some red team. It downloads a payload from a URL, does some decoding with it, can be arbitrarily complex. Here it's super simple, it's just base 64, and then stores the result in a member variable of this class. It then calls virtual alloc and create thread to execute that payload in memory. What do we need to dump this payload? So the first thing is the pointer to the buffer holding the payload that is passed to create thread as argument 3. And then, annoyingly, we also need the size of the buffer because there is no way in memory where it's stored in some metadata or anything like that. So we also need to do some haggling around with the virtual alloc function. There we want to first check get the second argument that is passed to virtual alloc and record it, and then store, and then remember that this is the length of the return value of the virtual alloc. So we need 3 places where we want to extract some data from the source code, and it's where these 4 arrows are. The first one, we want to get the second argument of virtual alloc. The second arrow, we want to remember the return value of virtual alloc, and at the third arrow, we want to see which buffer is actually executed by calling create thread. And we want to do that. That is what Tillmann mentioned in his third challenges slide. We want to just inject call instructions from our own analyzer. We call them gadgets. That's the thing. Yeah, we call them gadgets. And we want to inject call instructions at these 3 places that do what I just mentioned. So what you need to do that? You may need to make your analyzer class public. You need to implement a public gadget, and this gadget will just, and we will call the same gadget in all the 3 places. So we don't need to inject 3 gadgets for the 3 call sites. We just inject 1 gadget, and it will behave differently depending on the 2 arguments that the second argument that we pass, called T. In case 0, it's before the virtual alloc call, and in case 1, it will be directly after the virtual alloc call, and in case 2, it will be right before the create thread call. And the first argument the gadget receives is the actual value we want to capture. For the first arrow, that would be the argument passed to virtual alloc. For this case 1, it will be the return value. And for case 2, it will be the argument that is passed to create thread. And then we can look up the length of the buffer, copy it over, and dump it to the console. That's what's happening here. And this is the code that does the actual injection of the call instruction. So it looks a bit complicated on the left. We just get a reference to the gadget, because as Tillmann said, a call instruction also needs what is an operand of what is being called. That is constructed on the left. And then on the right, again, this is now the JIT interception code. We go through all the instructions, and when we see a create thread, we go back a couple of instructions and insert a dub, LDC2, and a call that will inject this gadget, and then it will first duplicate the top of stack, which is the variable we are interested in, then add a 2 to the stack to instruct our gadget to behave case 2-like, and then finally it will call the gadget. And the other two places are kind of similar. Okay, let's do this last demo then. And this is just a compiled version of the code that I showed you. And here we go. So we see here at the top, there is the disassembled bytecode again. Let me scroll up a bit here. And for example, there you can see the create thread call and a couple of instructions before it. You see the dub, LDC2, and call instruction. This call instruction doesn't know the name because dnlib only handles the assembly statically, and this call instruction is injected manually by our profiler, so it can't resolve the name. And then at the end, we just added fixed data to, because we didn't know if we had internet access or not, so this is the hex dump of the intercepted thread code. And this works generically now. Cool. And for a quick final words, I will pass it back to Sebastian, who will tie a bow on it and wrap it up.
Thank you, Lars. To wrap it up, Lars presented us first a simple demo of a profiler-based analyzer that just shows you function calls. Then Steffen also showed us that you could even use the nspice debugging functionality while running the profiler, so you can debug your target assembly and follow your code line by line. And later on, Lars demonstrated how we could modify the SIL bytecode one time using those regex with our target pattern language. And he also leveraged the nlib, so also very powerful. And then finally, we saw that you can even inject entirely new functions, these gadget functions, to enable the generic dumping of allocated buffers. Now, we're working on getting our code released, but it's still stuck in an internal process. So in the meantime, if you want to get access to the code, just speak to us or email us, and we'll figure out a solution. Thank you for your attention, and feel free to ask questions. Thank you.
So I think, I think we have a couple of minutes now, only not many, but do we have a microphone to pass around, or should I just repeat your question? Oh, but this is ours. Okay.
I'll handle that.
Okay. Thank you. If you also need to answer, you can just stay there with a microphone.
I don't think it's on.
No, it is.
I was wondering, what if the string decryption routines were inlined and there's no read function to hook? Do you address that case? Is something like Mandiant's floss, for example, just throw a binary, it figures it out. Do you handle such a case? And also, do I have to know the decryption routine every time, different variations, different protectors? Like, do I have to spend time, or just somehow give it any binary and profiling somehow figure it out? Because this doesn't scale if I have to go per variation or per family or something.
Okay, cool, thanks. So I will answer the second question first. I didn't fully get the first one, maybe one of you did. It's sadly not magic, so you still need to do some work. We started with targeting like commodity obfuscators, and they are relatively easy to signature the string decryption function and then just execute it on all samples with that obfuscator. No, but in general, it's not magic. There's still a lot of stuff you need to do. Our hope is, though, that we will slowly pile up more and more analyzers and then basically crowdsource it by having a lot of different analyzers. And the first question, did one of you get them? Get it? Okay.
If the strings were not, there's no function called encrypt, if everything was inline, like before, for example.
Yeah, okay, so that is kind of twofold. So first of all, you can, and this is what we currently do, when we start our profiler, it will tell the CLR to not do any inlining automatically. So it will be a method all the time. So we will get a dedicated JIT compilation callback for that method because it will never be inlined. We told the CLR to do. And even if it would be inlined, it would be inlined into an existing function. So it would be part of that parent function, so to say. And I think there are even in the profiler, there are callbacks for inlining. So you can get notified with the profiling callback API if the CLR decides to do any inlining. So if that isn't concerned, there would be a lot of possibility to catch these cases.
So it was just signaled from the back that we don't have time anymore. Is that correct? So I fear we need to wrap up, but we are still around. There were a couple of questions. Let's just answer them over coffee or later today. Cool. Thank you very much again.